Pleasant day to everyone. Today we're going to discuss part 3 of Module 6 for the subject C3151. So in this lecture, we are going to discuss the method of moments and least square. So another method that we use for curve fitting is what we call the method of moments. This is a method or a numerical method which uses both equations or derivation of equations and integration. So this works with a sample moment or a true moment and the theoretical or approximate moments of a line or a curve. This method would show discrepancy between the approximate and true values of the points both in linear and non-linear regression. For the method of moments, the following procedures are followed. So we first draw or derive preliminary equations of the moments, wherein we place the values of x and y, from which there should be the values of the mu and the gamma, wherein the mu is defined as a sample moment or the true moment of the equation, and gamma would represent the theoretical moments or the approximate moments of the given equation. So from here, we determine the coefficients A and B for the general equation of a line or a curve by either elimination or substitution. And once we are able to identify the coefficients of our equation, we may now proceed with the best fit line method. So for the method of moments, the procedure now will start off with identifying the value of each, which is equal to the difference of two consecutive x, wherein we assume that they are equally spaced. That is, x sub 2 minus x sub 1 is equal to that of x sub n minus x sub n minus 1. So once you have identified the value of each, we may now proceed with identifying our equations or our values for the moments. So we start off first with the first moment or the first true moment, which is given by mu sub 1 equal to h times the sum of y. For the second true moment, mu sub 2, that's equal to h times the sum of x, y. So the moments required would be dependent on the number of coefficients in the equation. So if we have a linear equation, which would have two coefficients, a and b, we'll only be needing the first and second moment. But let's say we have an equation of a curve with three coefficients, that is a, b, and c. We will be requiring now a third moment, mu sub 3, which is computed as h times the sum of x squared y. So once you have taken the values of the true moments, we'll now be able to move on to our theoretical moments, wherein we let y equal to f of x for any given curve or given line, which will give us the first theoretical moment, gamma sub 1, equal to the integral of y dx. The second theoretical moment as gamma sub 2 equal to the integral of x y dx, and the third theoretical moment as gamma sub 3 equal to the integral of x squared y dx. So once we have identified our true moments and your theoretical moments, what we have to do is to determine our final equations, wherein the true moment, mu, is equal to the theoretical moment, gamma. So we'll just simply equate your true moment with the theoretical. So for the first moment, that will now be equivalent to h times the sum of y equal to the function of x dx from the lower limit x sub 1 minus h over 2 to the upper limit x sub n plus h over 2. For the second moment, it will be given as h times the sum of xy equal to x times f of x dx from x sub 1 minus h over 2 to the upper limit x sub n plus h over 2. And lastly, for your third moment, that will now be h times the sum of x squared y is equal to the integral of x squared y, which is equal to f of x dx from the lower limit x sub 1 minus h over 2 to the upper limit x sub n plus h over 2. So for us to remember the equations for the true and theoretical moments, you could observe that the variable inside the sum or the sigma is the variable that is inside our integral equation for the theoretical moments. So basically, h is replaced by dx and the sum sign or the sigma sign is replaced by the sigma sign. And for the limits of our integration, for the final equations, it will be the same for all moments, which is given by x sub 1 minus h over 2 and x sub n plus h over 2. So to understand the method of moments, we solve an example. Given y equal to ax plus b, we determine the best curve that will fit the following data. So again, as we have said for method of moments, we have to start off first with identifying the value of h. So in evaluating now the values of x, we have x sub 2 minus x sub 1 is equal to 0.1. And if we continue further, we have x sub 3 minus x sub 2 is also equal to 0.1 as well. And if we are going to continue further, we are going to find out that the value of h for all the values of x is equal to 0.1. From here, we'll now be able to proceed with determining our true moments. For the first moment, that will now be mu sub 1 times h times the sum of y. So we have the value of h already. For the sum of y, we have 6.023. So substituting now the values of h and the sum of y, we get 0.6023. And then, looking up the given equation, we have only two coefficients, a and b. Therefore, we are only to determine until the second moment, which is now equal to mu sub 2 equal to h times the sum of x sub y. So for the x sub y values, we have to determine first the individual values of xy for each variable x, wherein for 0.1, we have 0.01002. For 0.2, we have xy equal to 0.04026. For x equal to 0.3, xy is 0.09135, followed by 0.16432, 0.26055, 0.38202, 0.53102, 0.71048, 0.92385, and 1.17520. So adding them up, we get a value of 4.28907. So substituting the values of h and x sub y, we get mu sub 2 equal to 0.428907. So from here, we now move on to determining the values of our theoretical moments. So for our theoretical moments, we were able to get the sum of x sub y is 4.2890. The value of h is 0.1. With the sum of x is 5.5 and the sum of y equal to 6.023. So for our first theoretical moment, it's now equal to gamma sub 1 equal to the integral of y dx, wherein y is equal to f of x. So substitute now the values of xn. Xn is 1, x sub 1 is 0.1, and h is 0.1. So fx now is equal to ax plus b. So if we're going to continue, gamma sub 1 now is equal to, or the integral of gamma sub 1 is equal to ax squared over 2 plus bx from 0.05 to 1.05. Or that is also equal to ax squared over 2 from 0.05 to 1.05 plus bx from 0.05 to 1.05. Substituting the values of our limits to the values of x, we have gamma sub 1 is equal to a over 2 times 1.05 squared minus 0.05 squared plus b times 1.05 minus 0.05, giving us gamma 1 is equal to 0.55a plus b. For the second moment, that is now equal to gamma sub 2 equal to the integral of xy dx. So substituting the value of x sub n, h over 2, and f of x, we arrive at the following equation. Gamma sub 2 is equal to the integral of x times ax plus b dx from the lower limit 0.05 to upper limit 1.05. So distributing x in our equation, we now have ax cubed over 3 plus bx squared over 2 from 0.05 to 1.05. We can distribute our limit to each term, and from there, we can now substitute our limit to the value of x in the equation, which will give us a over 3 is equal to 1.05 raised to 3 minus 0.05 cubed plus b over 2 times 1.05 squared minus 0.05 squared, giving us the theoretical moment gamma sub 2 equal to 0.385 raised to a plus 0.55 b. So once we have identified our true and theoretical moments, we now equate mu equal to gamma. So for mu sub 1, we were able to solve 0.6023, mu sub 2, 0.428646, gamma 1 is 0.55 a plus b, gamma 2 equal to 0.3858338 plus 0.55 b. So equating now mu sub 1 and gamma sub 1, mu sub 2 and gamma sub 2 will have equations 1 and equation 2. So we can solve this by solving it through elimination or substitution, and we'll be able to get the value of a and b as 1.1717 and negative 0.04214 respectively. So substituting the coefficients a and b in the given equation, so therefore, the best curve that would fit the data is given by the equation f of x is equal to 1.1717x minus 0.04214. Another example for the method of moments, given y equal to ax plus b, determine the best curve that would fit the following data. So for our solution, we first identify the value of h for our x. So we'll have now for all the values of x, we arrive at h equal to 1. So from here, we move on to identifying our true moments. So for the first moment, we'll now be required to solve first for the sum of our y, which is 16.9. For the first moment, mu sub 1, that's equal to h times the sum of y. So that's simply 1 times 16.9, which will give us 16.9. And then for our second moment, we are going to need the value of the sum of x, y. So for our given x's, we solve first for their values. So we have 0, 1.8, 6.6, 13.5, and 25.2, which will give us the sum of 47.1. So for the second moment, that is now equal to h times the sum of x, y, which is now equal to 1 times 47.1, which will give us mu sub 2 equal to 47.1. So we stop at the second moment since, again, in the given equation, we only have two coefficients. So next, we move on to solving the value of our theoretical moments. So for the first moment, that will now be the integral of y dx. So we are given x sub n is 4, h over 2 is 1 over 2, and x sub 1 is 0. F of x is y equal to ax plus b. So substituting those values, we'll now have 4 plus 1 half, 0 minus 1 half, ax plus b dx. Simplifying or integrating now exb, we have ax squared over 2 plus bx from the limits negative 0.5 to 4.5. Or that is now a over 2x squared from negative 0.5 to 4.5 plus bx from negative 0.5 to 4.5, which will give us now a value of gamma sub 1 equal to 10a plus b. For the second moment, that is now equal to the integral of xy dx, which will now be equivalent to the integral of x times ax plus b dx from lower limit negative 0.5 to upper limit 4.5. So if we are going to distribute x to ax plus b, we'll have ax squared bx, and integrating that, we'll arrive at gamma sub 2 equal to ax cubed over 3 plus bx squared over 2 from limits negative 0.5 to 4.5. So simplifying our equation, we'll arrive at a over 3 is equal to 4.5 cubed minus negative 0.5 cubed plus b over 2 times 4.5 squared minus negative 0.5 squared, which will give us gamma sub 2 equal to 30.4167 a plus 10b. So for our final solution, we'll have to equate our true equal to our theoretical. So for the true values of the moments, we have 16.9 and 47.1. For the theoretical values, we have 10a plus 5b and 30.4167a plus 10b. So equating mu sub 1 to gamma sub 1 and mu sub 2 to gamma sub 2 will arrive at equations 1 and equation 2. So solving this by substitution or by elimination by subtraction will now arrive at the values of A and B equal to 1.2768 and 0.8264 respectively. So with this, the best curve that would fit the equation y equal to ax plus b given the following data is the function of x equal to 1.2768x plus 0.8264. Another method that we use for curve fitting is the method of least squares. So this is a standard approach to approximate the solution of overdetermined systems. So an overdetermined system is a set of equations in which there are more equations than the unknown. The best fit result in the method of least square is assumed to reduce the sum of squared errors or residuals, which are stated to be the differences between the observed or experimental value and corresponding fitted value given in the model. The matrix method, the system of equations, and slope-intercept formula are all derived with the same principle of error in linear regression using method of least squares. So in curve fitting, we are to measure the error or the amount of error in our solutions. So as we have discussed in the overview or introduction of curve fitting, we have basically two methods of measurement. The first one is the maximum error given by the equation E sub infinity of f is equal to the maximum absolute value of the function of x sub k minus y sub k given the condition 1 is less than k less than n. So aside from the maximum error and the second method that we have discussed in the previous discussion, we also have what we call the average error, which is given by the equation E sub 1 of f is equal to 1 over n times the sum of the absolute value of the function of x sub k minus y sub k from k equal to 1 to n. While the last method now is what we call the root mean square, given by the equation E sub 2 of f is equal to the square root of 1 over n times the sum of the square of the difference between the function of x sub k and y sub k. So in the method of least square, what we're going to apply now in our analysis would be the root mean square, wherein we are going to use the minimum error, which is f of x sub k minus y k. The principle for the method of least squares would follow that the general equation of a line is given by y is equal to mx plus b, wherein y now is denoted as the function of x, the slope of the line is a, and the y-intercept is b. We likewise consider the error in RMS that we're going to minimize, which is E sub 2 equivalent to the sum of the squares of the difference of function of x sub k minus y sub k. And since f of x is equal to ax plus b, this equation now can be simplified or transformed into the equation e sub 2 equal to the summation of the square of ax k plus b minus y sub k. So this given equation now is minimized by calculus. So we are given two constants a and b. So what we are going to do is to apply partial derivatives or minimizing our error. And we start that with the partial derivative of e sub 2 with respect to a equal to 0, which will now be equivalent to the sum of 2 times the quantity a x sub k plus b minus y sub k multiplied to x times or x sub k. Simplifying will arrive at the next equation, the sum of the quantity ax squared plus bx minus xy equal to 0. Further simplifying the equation, we can now equate that the sum of ax squared plus bx is equal to the sum of x times y. The next derivative will be taken from the partial derivative of e sub 2 with respect to b equal to 0. So in this case, we'll have the summation of 2 times the quantity ax sub k plus b minus y sub k times the derivative of b, which is 1, is equal to 0. Simplifying this equation, we now arrive at the sum of axk plus b minus y sub k. We can simplify this further again by distributing the sign summation to axk plus b and y sub k. Thus, we'll arrive at the equivalence between the sum of x sub k plus b and y sub k. The first way of solving the best curve using method of least squares is using matrices. From the two equations that we have derived from the previous slide, we transform this into a matrix form to unknowns a and b. So we'll arrive at the first equation of a 2 by 2 matrix. So from here, we could denote that the first matrix is A, second matrix is X, and last matrix is B. So this matrix now can be written as AX equal to B. To solve for the unknown X or vertical matrix AB, we extract X and arrive at the equation X is equal to the inverse of A multiplied to B. The second method that we use for determining the best curve using method of least squares is using the systems of equations. So given the equation of a line y is equal to ax plus b, we account for all the values in the given data set, wherein we have the sum of y is equal to the constant a times the sum of x plus n times b, which will be equation number 1, and multiplying the whole equation by the sum of x, we arrive at the sum of xy is equal to a times the sum of x squared plus b times the sum of x, which will be our equation 2, in which equations 1 and 2 will be our working equations for the method using system of equations. The third way of solving for the best curve using method of least squares is using the slope-intercept formula, which gives us y equal to mx plus b as its general form. So in this method, what we will do is to use the equation of M taken from statistics is equal to N times the sum of the product of xy minus the sum of x times the sum of y all over N times the sum of x squared minus the square of the sum of x. And from here, we'll be able to get b as equal to the sum of y minus m times the sum of x all over n. Once we have solved for the values of m and b, we simply substitute it in the equation of the slope-intercept form, thus giving us the equation that would best fit the given dataset. This equation or this method is also referred to as the ordinary least squares or OLS. So to understand method of least squares by using system of equations, let us try solving example number 1. So given the equation y equal to x plus b, let us determine the best curve that will fit the following data. So for the method of least squares using system of equations, we have given that we're going to use equation 1, which is the sum of y equal to a, times the sum of x plus n times b, and equation 2, which is the sum of xy equal to a times the sum of x squared plus b times the sum of x. So from this equation, what we're going to need is the value of y, or the sum of y, the sum of x, which can be taken from the given table, and that is now equal to 5.5 and 6.023. And then next, we need the value of n, which is equal to 10, or this is now the number of points or the number of data sets or data in our data set. Then next, we have for equation 2, we need the values of xy and x squared for each variable. So we'll have now xy is equal to 0.01002 when x is equal to 0.1. Then we have 0.04026 when x is equal to 0.2, 0.09135, 0.16432, 0.26055, 0.38202, 0.53102, 0.71048, 0.9235, and 1.17520, giving us a total of xy, which is equal now to 4.28907. And for x squared, we'll have the following values: 0.01, 0.04, 0.09, 0.16, 0.25, 0.36, 0.49, 0.64, 0.21, and 1, giving us sum of x squared as 3.85. So given now all the necessary values that we need for our equations 1 and 2, just substitute these values, arriving now at 6.023 equal to 5.5a plus 10b, which gives us equation 1a, and 4.28907 equal to 3.85b plus 5.5b, giving us equation 2.8. So given now these two equations, we can solve it by either substitution or elimination, and it will give us a value of a, which is 1.18854, and b equal to negative 0.04865. So meaning, the equation now that would best fit our given data is f of x is equal to 1.18354x minus 0.04865. Another example for the method of least squares using system of equations, we have for the given data, we trace the best curve for the equation y equal to ax plus b. So again, for systems of equations, we know that we are going to use equation 1, which is equal to the sum of y equal to a times the sum of x plus n times c. And for equation 2, that is now given by the equation, the sum of xy equal to a times the sum of x squared plus b times the sum of x. So for equation 1, we are going to need the values of the sum of x and y. In this case, we have 10 and 16.9. For equation 2, we are to solve for the values of x, y, and x squared for each values of x, in which it will give us a total value of xy of 47.1, and we have the sum of x squared will be equal now to 30. So given the values of the sum and a total number of data points, which is equal to 5, we can now substitute this in the equation 1 and 2, in which we are going to arrive at 16.9 equal to 10a plus 5b, and 47.1 equal to 30a plus 10b. So in this case, we can now solve for our coefficients a and b by substitution or elimination. In this case, we are going to use elimination by subtraction. In order to eliminate b in the equation or in the two equations, we multiply it by 2. With that, we'll now arrive at negative 13.3 equal to negative 10a, which will give us a value of a equal to 1.33 and a value of b equal to 0.72 by substituting a in either equation 1 or 2. So, meaning, given now a and b, the best curve that would fit our given data will be f of x is equal to 1.33x plus 0.72. For the method of least squares using the slope-intercept or the OLS method, for the given data, we are to determine the best curve for the equation of form y equal to ax plus b. So the slope-intercept form is given, or the general form of the slope-intercept is given by y equal to mx plus b. So in here, for the method of least squares, we are going to solve for m as equal to n times xy, the sum of xy, minus the products of the sum of x and y all over n times the sum of x squared minus the square of the sum of x. And for the y-intercept, this will now be computed as the sum of y minus m times the sum of x all over n. So we are going to need again the value of the total number of points or data points in our data set. And in this case, we have 10 values of x or 10 set of points. And for our m and b, we're going to need the value of x, y, and x squared in order to get this value of the sums. That is now for the sum of x, that's 5.5. The sum of y is 6.023. Sum of xy is 4.28907. And x squared is 3.85, which we have already solved in the previous examples. So substituting the value of n and the value of the sum of xy, x and y, and x squared, we can now solve for m as 10 times 4.28907 minus 5.5 times 6.023 all over 10 times 3.85 minus 5.5 squared. And for the y-intercept, it will now be 6.023 minus our computed m, which is 1.18354 times 5.5 all over 10, giving us the value of the intercept as negative 0.48647. So given now m and b, substitute this in the slope-intercept form equation. So the equation now that would best fit our data is f of x is equal to 1.8354x minus 0.48647. And if you're going to notice, this is exactly the same equation that we have solved using the system of equations. So another example for the slope-intercept or the OLS. So for the given data, again, the slope-intercept form is given by the general equation y equal to mx plus b, wherein m for the slope-intercept using method of least squares is equal to n times the sum of xy minus sum of x times sum of y over n times the sum of x squared minus the square of the sum of x. And b, or the y-intercept, is equal to the sum of y minus m times the sum of x over n. So from the given data, we have a total of 5 data points. We will need now the values of x, y, and x squared in order to get the value of the sum of x, y, xy, and x squared, which is 10, 16.9, 47.1, and 30 respectively. Again, we have already solved this in the previous example. So from here, we now substitute the values of the sums and the value of n in the equation of the slope and y-intercept, wherein m now is equivalent to 1.33, and for b, substituting now the sum of y and sum of x and the computed m, we now arrive at b equal to 0.72. Therefore, the equation that would best fit the given curve of the following data is f of x is equal to 1.33x plus 0.72. So if you're going to notice again, it is exactly the same as the equation that we have derived using the method of least squares by the system of equations. So that's it for curve fitting using method of moments and least square method. Thank you for listening.